And one more thing, I will share the slides soon.
Yeah.
Okay, so I am very glad to present Emile Okada from Oxford and announce his talk on the Wavefront set of representations of p-adic groups.
Thank you. Thank you for inviting me to give this talk, and thank you everybody for attending. Like Dima mentioned, I'm going to be talking about the Wavefront set of representations of a p-adic group, and I'll also present some recent research by Dan Ciubotaru and Luke and Mason Brown, where we connect this to Arthur packets. All right, so without further ado, let me begin with some motivation. So the Wavefront set is an invariant that you can attach to representations of a reductive group and over various rings, so either of the adels of a number field or finite field extensions of the real numbers, like the p-adic numbers or finite fields. And it's an invariant which consists of a collection of nilpotent orbits. And even though there are various definitions in each of these cases, and in fact, I should mention, going back, there's sort of various candidates for what you might want to call the Wavefront set in each of these instances as well. There's sort of the definition for nilpotent orbits over the base field, and then there's also nilpotent orbits over the algebraic closure of the base field. So I call the one corresponding to the algebraic closure the Wavefront set. So, and there's non-trivial interplay between these various invariants. And this is this particular inequality Dima here is an expert on. So if you have a irreducible L2 automorphic representation, the Wavefront set of the automorphic representation lower bounds the Wavefront set for the local factors. And in this talk, the relationship between the p-adic Wavefront set and the finite field Wavefront set will feature very prominently. And it's quite a powerful invariant. The main reason being it's quite often dual to some notion of a unipotent or a nilpotent parameter. But it has the benefit that it sort of lives on the original side. So the unipotent parameter often lives on a dual group. So if you take the FP Wavefront set, for instance, where a lot is known due to Lustig, if you take, for instance, the classification of irreducible representations of the finite group of Lie type, that's in terms of some of the geometry on the dual side. And there's often there's a nilpotent parameter you can attach to it due to that classification. And then due to a result by Lustig, the Wavefront set is in some notion dual to the unipotent parameter there. And like I said, it lives on the original side. And so it has the benefit of providing a natural way to control the unipotent parameter. So this invariant is quite powerful for that reason. And an example sort of illustrating this, and an example which motivated a lot of the research of Dan, Lucas, and myself was the example of unipotent Arthur packets in the complex case. So these unipotent Arthur packets are expected to be sort of the building blocks of the unitary representations. And what Barbash and Vogan did in '85 was they defined these unipotent Arthur packets in terms of the Wavefront set. So let me just briefly outline these results without sort of going too much into the details of the notation. But if we like pi sub lambda denote the set of irreducible representations with infinitesimal character lambda, and if we let O check be some nilpotent complex orbit, and H check be the neutral element for that orbit. So if you included an if you take an SL2 triple for O check, then H check is the neutral element. Then what Barbash and Vogan showed in '85 for even orbits, and which Lucas, Losev, and Matveyevsky showed for generalized to all orbits, was that these representations have a lower bound. The Wavefront set has a lower bound by the Barbash-Vogel dual of O-check. And I call it the Barbash-Vogel dual here. This duality map was originally discovered by Spaltenstein, but it was sort of defined sort of case agnostically in the complex case by Barbash and Vogel. And I believe a lot of the researchers in this area refer to it as the Barbash-Vogel dual map. And then because of this lower bound, they defined the Unipotent Arthur packet to be the representations with this infinitesimal character and Wavefront set equal to the dual of O-check. And these representations are then expected to be the building blocks. So that's sort of the motivation for why one might be interested in the wavefront set as a representation. In this talk, I'm going to be talking about the p-adic wavefront set. So without further ado, let me define what that is and introduce some notation. So we're going to always be working with a split case here. So we're going to let G denote a connected reductive algebraic group defined over the integers. And we're going to let G check be its Langlands dual group. And we're going to write G and G check for the complex points of these groups respectively. And we're going to be interested in a finite extension of the p-adics. We fix some algebraic closure K bar. And then K is going to be the maximal unramified extension inside of this. So there's a lot of fields, but the main role of the maximal unramified extension really is the fact that if you take the ring of integers, then the residue field is an algebraic closure for the residue field of K. So like I mentioned, nilpotent orbits will feature prominently. So let me introduce some notation for that as well. So we're going to let n denote the functor which takes a field to the set of nilpotent elements of the f points of the Lie algebra. And we're going to write n sub O for the nilpotent orbits. So there's an adjoint action on the nilpotent elements, and n sub O refers to the nilpotent orbits. When f is algebraically closed, we of course have the Zariski topology on the Lie algebra, and we want to view the nilpotent orbits as a partially ordered set with respect to the closure ordering. So by which I mean an orbit is considered less than another orbit if it lies in the closure. When f is either the p-adic field or the maximal unramified extension, we want to view it as a partially ordered set with respect to the closure ordering again, but the topology is the one induced from the topology from K or capital K. So these have a p-adic topology, and that gives the Lie algebra a p-adic topology as well. But this is all sort of technical. All you need to know is that it's a partially ordered set. And when we want to emphasize the group, we include it as a superscript. And when the group is G check, we just write G check. And finally, if we're looking at C points of something, we usually just omit the field for notational simplicity, just like the C points of the group. And if you remember in the first slide, I sort of had a quotation marks on the lower bound because sort of the wavefront set nilpotent orbits, they live over different fields. But this result due to Pomeranning states that sort of provided that the characteristic is large enough and you're working over an algebraically closed field, the partially ordered set of nilpotent orbits is always just the same as over the complex numbers. And we denote this identification as theta f. So that simplifies the situation in a lot of instances. Okay, so that sort of is the preliminaries. Let me define for you the p-adic wavefront set. So we start with some irreducible smooth representation, and the definition goes via the so-called Harishchandra and Howe local character expansion. And what that does is it relates the character distribution of X to certain distributions on the Lie algebra. Without getting too much into the details, let me briefly describe how you get the wavefront set from this. So the character distribution of X is just the p-adic analog of the character representations of finite groups. And that's how you should think about it. And to sort of relate it to the distributions on the Lie algebra, we need an exponential function. And we do have this in the p-adic setting, but we only have it defined locally. And what the Harris-Chandra and Howe local character expansion does is it relates the character distribution to these Fourier transforms of nilpotent orbital integrals. So it says there's an open neighborhood of the identity such that when you restrict the character distribution, you can write it as this linear combination. And it's not so important what this is. It's just sort of for every nilpotent orbit, there's a way to attach a measure on it. And then sort of you get a distribution just by restricting the function. And things converge. That's an issue, but it doesn't need to worry about this in the p-adic case. The key thing is that the nilpotent orbits sort of feature in this distribution. And the p-adic wavefront set is just defined to be the maximal orbits which occur in this expression. And this is actually quite a difficult invariant to compute. The sort of most general result I'm aware of was proved in 87 by Langlands and WIS where they did it for GLN and subquotients of the regular principal series for split classical groups. Now there's another notion of a wavefront set you can attach to p-adic representations, which I alluded to in the motivational section of this talk. There's always sort of two things you can do. You can either work over the field itself or the algebraic closure of the field. Now, and so this other one relates to the algebraic closure. So every p-adic orbit lies inside of a geometric orbit just by sort of saturation. And so the geometric wavefront set is defined to be the largest geometric orbit, which arises in the Harris-Chandra and Howe local character expansion. And the reason why this is a very sort of reasonable invariant to consider is it's conjectured that all of the p-adic wavefront set nilpotents lie in the geometric wavefront set. So it's conjectured, first of all, that the geometric wavefront set is a single nilpotent orbit, and all the p-adic ones lie inside of it. And this is a theorem in the real case. They all lie in a complex orbit. And this is much more manageable to compute. And whilst Berger computed this for anti-tempered and tempered representations of pure inner twists of SO2n+1. And he did this in 2018 and 2020 respectively. And what's quite nice and striking about his results, which he presents very nicely in the anti-tempered case, is he relates the wavefront set to the local Langlands correspondence. And so it's a manifestation of this phenomenon that I described earlier, that the wavefront set is in some sense dual to the unipotent parameter attached to X. So for that, let me introduce some notation. So if you have some irreducible smooth representation of a split p-adic group with this L parameter phi, we're going to write O check of X for the orbit corresponding to this SL2 under the Jacobs and Morozov theorem. So if you're familiar with that, that states that conjugacy classes of SL2 homomorphisms are in bijection with nilpotent orbits. And this is an explicit description of what that orbit is. We also need to introduce some dualities. So the Verza-Levensky dual of X it's a duality on the Grothendieck group of smooth representations for the p-adic group. And D here is the Spaltenstein dual, which I called earlier the Barbash-Vogel dual, which I'll call the Spaltenstein dual in the rest of this talk. And we view it now as a map from nilpotent orbits in the complex dual group to geometric orbits on the p-adic side. And we do this by just identifying these two using Pomeranning's map that I mentioned earlier. And then what Berger showed was that the anti-tempered representations have a very nice description of the geometric wavefront set, and it's given by this equation here. And it's tempting that this is always the description for the wavefront set for smooth representations, but this isn't always. This isn't true even for anti-tempered representations. So if you take G to be E7 or E8, then there are anti-tempered representations where this equality doesn't hold. So you can show that for allIwahori-Spherical representations, there's always this inequality. And But in E7 and E8, this inequality can become strict. So somehow the geometric wavefront set isn't sensitive enough to interact nicely with the local Langlands correspondence. And this is sort of where some of my latest work comes in. I defined the canonical unramified wavefront set in my preprint that came out earlier this year. And it's sort of a refinement of the geometric wavefront set. And it sort of seeks to rectify the situation. The aim is sort of that it interacts nicely with the local Langlands correspondence. Okay, so for the middle part of this talk, the goal is to define what this canonical unramified wavefront set is. But to do this, I'll need to introduce some auxiliary concepts. So first of all, I'll need the Broussard-Titz building. And for those of you who are unfamiliar with what that is, this is just a simplicial complex which you can attach to a p-adic group. The p-adic group acts on it by simplicial morphisms. So for the sake of this talk, we assume semi-simple and irreducible root system. Otherwise, we would need to include poly in the description, but in this case, it's just a simplicial complex. And the Broussard-Titz building is formed by gluing together so-called apartments. So you have an apartment for every split maximal torus, and an apartment is formed by taking the co-root lattice and tensoring it with the reals. So that gives you a vector space, and then to turn it into a simplicial complex, you sort of chop it up with hyperplanes, where every hyperplane corresponds to the integral vanishing of some root. So if you take, for instance, so this is an apartment for SP4 QP, and if you take the vanishing of alpha 2, that's this hyperplane here. If you take the vanishing of alpha 2 minus 2, that's this hyperplane. And if you do this for all the roots in your root system, you can turn the apartment into a simplicial complex. And like I said, you glue them together, but for the sake of this talk, it's sufficient to consider a single apartment. Okay, so what do we need from the Broussard-Titz building? Well, we need these so-called Parameterisation subgroups. And if you recall, since we act by simplicial morphisms of the building, we can form the stabilizer of a facet of the building. This is defined over the ring of integers for the p-adic field. And we can form the special fiber, and that's some reductive group. And we fit this into a short exact sequence as follows. Now, it's not so important, this full reductive group. We're really interested in the identity component of it. And the Parameterisation subgroup is sort of the inverse image of the identity component. And like I say, these are the so-called Parameterisation subgroups. And in case this is mysterious, here's just some examples of Parameterisation subgroups and their reductive quotients. So going back to the SP4 example, if we take C0 to be the origin of this apartment, then, and this is the apartment corresponding to diagonal torus in SP4, then the Parameterisation subgroup is just the integral points of SP4, and the reductive quotient is just SP4 over FP. So this is not too interesting. Slightly more interesting example is the case when you take this vertex here, C1, then the Parameterisation subgroup attached to this facet is this mysterious looking matrix, but the reductive quotient has a very nice form. So if you're familiar with pseudo levies, this is just SP2 cross SP2 embedded in SP4. And this has root system A1 cross A1. And if you look at the hyperplane arrangement going through C1, that is exactly the hyperplane arrangement of a root system of A1 cross A1. And this is no coincidence. So if you choose some system of simple roots and you let alpha naught be 1 minus the highest root, then you get this so-called extended Dynkin diagram. And if you take the chamber cut out by these extended simple roots I've included here, this is one of this triangle here, and label each facet by which extended simple roots vanish on it. So this is the vanishing of alpha 1 and alpha 2. This is the vanishing of alpha 2. Then you can read off the root system of the reductive quotient by just taking the extended Dinkin diagram, and taking the subgraph spanned by those labels. So in this vertex here, subgraph spanned by alpha 1 and alpha 2 is a Dinkin diagram of type C2, which is the root system of SP4. And if you take this facet here, that's alpha 2 is the only thing that vanishes on it. And subgraph spanned by alpha 2 is type C1 or A1, which is the root system of this. Okay. So why do we need the Broussard-Titz building? So I mentioned all these different notions of wavefront sets. They're all related to each other. And in particular, the p-adic wavefront set is related to the wavefront set over the finite field. And this Broussard-Titz building has given us a gadget, so to speak, to relate to finite field objects. So the reductive quotients are defined over the residue field. So we need a way to sort of lift nilpotent orbits from the reductive quotient up to the p-adic space. And so let me briefly define to you how this lifting process works. So if we start with some facet of our building and the nilpotent element of the reductive quotient, then if you recall the short exact sequence from earlier, there's a map on the level of Lie algebras, and we can consider the pre-image in sort of the Lie algebra of the parameteric subgroup of this nilpotent element. This is some coset. And then a theorem of Barbash, Moy, and de Backer states that there is a nilpotent orbit which intersects this coset, and in fact there's a unique minimal one. So remember this partial ordering on the nilpotent orbits. And we define this unique minimal element to be the lift of y, and we denote it by L C of y. And to give a couple of examples again, if you take the vertex corresponding to the origin of this apartment, and you take x to be this nilpotent element here, then the lift is just the matrix that looks the same, but here one lives in the p-adic field rather than the finite field, and it's the orbit of this. And for a slightly less trivial example, again, let's return to the case where the facet corresponds to this vertex, and we take the nilpotent element to look like it's the same nilpotent element, but here it lives inside of this group instead. Then the lift, it has the same Jordan decomposition, so it lies in the same geometric orbit, but there's now this p inverse, so it doesn't lie in the same p-adic orbit anymore. So this lifting process genuinely gives you interesting p-adic orbits. And it has sort of the expected properties that you'd expect from lifting. If x and x prime are in the same orbit, then the lifts are going to be the same. And so this gives us a map from the set of all pairs, C, O, where C is a facet and O is a nilpotent orbit of the reductive quotient, to the set of p-adic orbits. And this is a surjective map. And this was originally proved by Barbash and Moy in 1997 and proved later in much larger generality by de Backer in 2002. Okay, so this defines a lifting procedure for orbits from the residue field of the p-adic field. Like I mentioned, we really want to, the wavefront sets we're interested in are defined over the algebraic closure. And so we want a lifting procedure from here to here. And this is, you can do this exactly analogously, and I do this in my 2021 preprint on the archive. You can similarly just lift F bar rational orbits to unramified orbits. And it's precisely the same procedure. So we define this lifting operation from pairs C, O, by where O is now a geometric orbit of the reductive quotient. And this gives us a map to unramified orbits. Okay, so this is sort of all the tools that we need to define the first approximation of this canonical unramified wavefront set that I've described. And it goes as follows. We need these so-called local wavefront sets first. And to do it, we attach to every facet. So first of all, there's this procedure. If you have a facet of the building, you can take the space of invariance of your representation with respect to the pro-unipotent radical. And this gives you a finite dimensional representation of the reductive quotient. And like I mentioned, there's a notion of a wavefront set for reductive groups over a finite field. And it's also known as the Canonical wavefront set because Canonical was the first person who defined it in this setting. And we defined local wavefront set at C to just be the lift of each of the orbits in the Canonical wavefront set of this representation. So this gives us some collection of nilpotent orbits over the maximal unramified extension of little k. And so now we define the unramified wavefront set, so not quite the canonical unramified wavefront set, to be just the maximum over all these local wavefront sets. So you take every facet of your building and you lift all the Canonical wavefront sets and you define the maximum of these orbits to be the unramified one. And in my preprint, I show that this coincides with sort of the natural notion of what one might call the unramified wavefront set. So it coincides exactly with the largest unramified orbits, which arise in the local character expansion. There's sort of two sort of issues with working with the unramified wavefront set. The first one is there's no really nice description of the unramified nilpotent orbits. So when you're working over K bar, there's this result of Pomeranning. We can just work over C. But for capital K, there's no nice description. And this partial ordering on the nilpotent orbits is also very poorly understood. And so to rectify both of these issues, in my paper, I provide a parameterization of the unramified orbits. And the parameterization is very similar to parameterizations of other kinds of nilpotent orbits that you might have seen. Now, I'll refer to that briefly in a bit. But first, let me introduce some notation. So NOC, here O refers to orbit and C refers to conjugacy class, is a set of all pairs O, C, where O is a nilpotent complex orbit, and C is a conjugacy class of the component group of the centralizer of an element of O. And then the description, the parameterization of the unramified orbits that I give is in terms of this set NOC. So there's a canonical bijection from these unramified nilpotent orbits with NOC, and it's compatible with sort of natural maps. It was compatible with Pomeranning's parameterization of the geometric orbits. So every unramified orbit lies in the geometric orbit, and there's a natural projection map onto the first factor here, and this diagram commutes. And for those of you who are familiar with nilpotent orbits, there's an analogous parameterization of the FQ rational nilpotent orbits of the split reductive group over FQ in terms of NOC, but over FQ bar. But this parameterization differs from that parameterization in the sense that it's canonical. So in this case here, in the FQ case, you need to choose a base point, and then the parameterization is relative to that base point. So the trivial conjugacy class corresponds to your chosen base point, and then sort of other conjugacy classes are sort of like paths to other ones. It's relative to that. But this bijection is completely canonical, so it doesn't require a choice of base point, and the trivial conjugacy class always corresponds to a particular unramified orbit. There's no choice involved.
Could you please remind the notation, what is big K?
Sorry?
Could you please remind the notation, what does big K mean?
Oh, yes. So big K is the maximal unramified extension. So it is, it fits into this diagram. It's the one, you're drawing all the roots of unity of little k. And you get.
I see.
So every unramified extension of K embeds into capital K. Well, yeah.
Thanks.
So this is a field that sort of crops up quite naturally, quite a bit in representations of p-adic groups. Yeah, and the crucial property is this. The residue field is an algebraic closure. Okay. So that addresses the first issue that I mentioned, which was understanding a parameterization of the unramified orbits. But it doesn't address this other issue that I mentioned, which was understanding the partial order. And as far as I'm aware, that's fairly wide open still, what that looks like. But this parameterization actually provides a very nice resolution to that issue. So in 2001, Summers defined this map, a duality map, which is a natural extension of this Spaltenstein duality map that I mentioned before, which goes from these pairs NOC to nilpotent orbits of the complex dual group. And Achar later on in 2003 used this map to define a pre-order structure on this set here. And it's a very simple, intuitive pre-order. It's the finest pre-order which makes this duality map of Summers order reversing and this first projection map order preserving. In symbols, it's just this here. And what's quite striking is that this parameterization that I've mentioned is not an isomorphism of pre-orders. So it's conjecturally, it is a morphism of pre-orders. So conjecturally, if you have an orbit is less than the other here, then you will have an order less than the other in the sense of Achar. But it cannot possibly be an isomorphism of pre-orders. The reason being, this is a partial order, but the pre-order on this is definitely not a partial order. And to see this, this was again work done by Achar. We let NOC bar denote the set of all pairs O, C bar, where O is a complex nilpotent orbit, and C is a conjugacy class of Listic's canonical quotient of the component group. And this is in the sense of Summers again. So Listic only defined the canonical quotient for special orbits and an adjoint type. But Summers extends this definition to arbitrary orbits in any isogeny. Then in particular, what Achar shows is that the equivalence classes with respect to this pre-order are exactly the fibers of this map. So there's a natural map from NOC to NOC bar, just coming from the fact that the canonical quotient is a quotient of AOs of the component group. So if you have a conjugacy class of the component group, you certainly obtain the conjugacy class in the quotient. But crucially, this pre-order is very simple to compute. And so if we transfer this pre-order to the unramified orbits using this parameterization that I've given, then this defines, of course, first of all, an equivalence class on the unramified orbits. And on the equivalence classes, it defines partial order by simply just identifying this with this set here. And if we use this partial order instead of the pre-order partial order on the natural partial order on the unramified orbits, everything becomes a lot more manageable. So we're going to write square brackets to denote equivalence classes. So using, and there's also the additional benefit that these things come with a duality map known as the Achar's duality, which extends Summers's duality even further. And this will become relevant shortly. But now with these notions, we can finally define what the canonical unramified wavefront set is. It is just the exact same thing as the unramified wavefront set, but where we take equivalence classes instead of just unramified orbits. And the maximum is computed with respect to this Achar partial ordering. So this sorts out the issue, both issues mentioned earlier, describing unramified orbits and the partial ordering. And there's this additional result from my preprint, which says you can also compute this invariant by just restricting to a single chamber of the building. So a priori, this maximum is over infinitely many facets, but you can just restrict to the facets of a single simplex, if you will, and you can compute it in this way. And then this new invariant is a refinement of the geometric wavefront set in a very natural way. So if we write comma C to denote the same invariant, but sort of transferred along using the two identifications I've described, then whenever the canonical unramified wavefront set is a singleton, the geometric wavefront set is just the first component of the unramified wavefront set. So you remember these are pairs. The geometric one is just the first entry. And if we drop the requirement that it's a singleton, there's still a very straightforward relation between the two. But in all the cases, we consider it's a singleton, and so we have this very simple equality. Okay, so equipped with this new invariant, we can fix some of the issues that came up in these examples in E7 and E8 that I described earlier. And if we look at those examples, sort of the takeaway is that the relationship between the unipotent parameter and the unramified wavefront set should be this equality. And this, if this were to hold, this would also perfectly explain why there's no issue in SO2m plus 1, and why there is an issue in E7 and E8. So one always has that this inequality holds. And so by applying Spottenstein duality to this equality, we obtain this upper bound. And then the reason why there are discrepancies in E7 and E8, but not in SO2m plus 1, has to do with in what way this inequality becomes an equality in certain situations. So it reduces this issue to a statement about studying the partially ordered set of nilpotent orbits, really. And one more remark is that it allows you to perfectly recover the unipotent parameter from the unramified wavefront set, which sort of is more in line with this philosophy that I mentioned, that the wavefront set is naturally dual to the unipotent parameter of a representation. Right. So let me now go on to describe some results that Dan, Lucas, and myself have done in computing this invariant. And to do this, let me just introduce some notation again. So let me just recall the parameterization of representations with unipotent cuspidal support. So they're parameterized by these triples Sn rho, where S is a semi-simple element and satisfies this equality, and rho acts as the identity. Then we have this parameterization of these representations by these triples. So we're going to write X, S, and rho for the corresponding representation. And I'm also going to introduce some terminology. I'm going to call S the infinitesimal character of the representation. In the real case, there's a notion of infinitesimal character. In the p-adic case, S often plays that same role, which is why we call it the infinitesimal character here. And we can always assume it lies in the complex dual torus, since we're considering these triples up to the conjugation. And we also want to define sort of this notation, pi sub S. That's all the representations with S as infinitesimal character. And we say X has real infinitesimal character if S lies inside of the real part of the torus. So I suppose the state of the art in computing the canonical unramified wavefront set is the following, where if you take X to be an irreducible smooth allIwahori-Spherical representation with real infinitesimal character, then the canonical unramified wavefront set is first of all a singleton, and it can be given in terms of the Achar dual of O check, the trivial conjugacy class. And in particular, this verifies this conjecture that I mentioned earlier, and the geometric wavefront set here actually coincides with this expression that WIS Representation found in essay 2n+1. So naturally, these counterexamples that I mentioned earlier do not have real infinitesimal character. Okay, so that sort of hopefully convinces you that the canonical unramified wavefront set is the correct notion, or the natural notion to look at when you're looking at p-adic representations, and really is the invariant that behaves well with respect to the local Langlands correspondence. Let me briefly switch gears and sort of explain to you why we computed these identities, and sort of the motivation comes from the motivation I gave earlier in the second slide, which was to define these unipotent, to define some unipotent Arthur packets. So in the Barbash and Vogan in 85, like I mentioned earlier, defined these Arthur packet in terms of the wavefront set, and we were hoping to do the same thing for the p-adic groups. So define these building blocks for the unitary representations. And I'll give an example shortly, but let me first state the results that we have. So if we have O check again is some complex nilpotent orbit, and H check is the neutral element which lies inside of the real torus, then we obtained exactly analogous bounds on the wavefront set as what Barbash and Vogan did. So if X has infinitesimal character Q to the 1/2 H check, so here Q to the 1/2 H check plays the analogous role of the 1/2 H check in the complex case, then we have this lower bound on the canonical unramified wavefront set. And if you apply the projection map, we obtain a lower bound on the geometric wavefront set as well. So this exactly mirrors the complex case. And so we can define exactly an analogy. In analogy to the complex case, we can define this packet attached to O check, and we define it to be all the wavefront sets which have this minimal canonical unramified wavefront set. And the result we obtained is the following. So suppose X is some allIwahori-Spherical representation with this infinitesimal character, then X lies inside of this packet if and only if the Oberzer-Lewinsky dual of X is tempered. And so in particular, one gets immediately from this, since tempered representations, the unitary, that X is unitary, since this preserves unitarity. And we have a very nice description of this packet in terms of this set, at least for the allIwahori-Spherical ones. Now I should point out that all of the results which I've stated, we expect to hold without without the requirement that it's allIwahori-Spherical. We expect this should hold for all representations with this infinitesimal character, in which case the packet would just be described by the irreducible representations of this component group. This restriction that it's of Springer type is just to pick out the allIwahori-Spherical ones. And so let me quickly give an example of this. Sorry, actually, let me just, so that defines a packet. Let me actually first put it in the context of Arthur's conjectures. So let me give you the Arthur parameters, which should parameterize this packet. So quickly just recall Langlands variation of the Wedelin group. So that's just the Wey group when K is Archimedean, and the Wey group cross SL2 in the non-Archimedean case. And recall that Arthur parameters are these continuous homomorphisms into G check, satisfying certain conditions. So the restriction to the Wavefront group is tempered, and the restriction to SL2 is algebraic. And we consider these parameters up to conjugation on the target. Then Arthur's conjectures, or Arthur posits that to every such Arthur parameter, one should attach a finite set of irreducible admissible representations called the Arthur packet attached to psi. And this needs to satisfy some desiderata, which I won't go into. And so to put the packet that we described earlier into this context, they should correspond to these so-called anti-tempered parameters. So they're the parameters which are trivial on the Wavefront group. And in a sense, they're as far from tempered as possible. And then by the Jacobs and Morozov theorem, like I mentioned before, conjugacy classes of SL2 homomorphisms correspond to nilpotent orbits. So we attach pi check to the parameter corresponding to that nilpotent orbit, the anti-tempered parameter that corresponding to that nilpotent orbit. So now let me give an example to illustrate what happens. So let's consider the case where G is of type F4 and O check is the minimal distinguished orbit. So I've listed here all the representations with infinitesimal character given by the neutral q to the 1/2 of the neutral element of O check. And I've listed the canonical unramified wavefront set in this final column. And I've listed all the duals here. And I've highlighted all the representations with minimal canonical unramified wavefront set. And what's quite striking is you can tell, and is a feature of the theorem that I mentioned earlier, all the ones with minimal canonical unramified wavefront set are the AZ dual of tempered representations. So the tempered representations amongst these are the first 5. And as you can see, the green ones correspond to X1 to X5. If we highlight all the representations with minimal geometric wavefront set, we get a lot more representations. They're all still unitary, but they're no longer the AZ dual of the tempered representations. And there's no sort of obvious parameterizing set for this. It's not obvious indeed that it should consist of a single Arthur packet, which is why canonical unramified wavefront set seemed the more natural choice. It provides the exact analog of what happens in the complex case. But nonetheless, in analogy to what happens in the real case, we define the weak Arthur packet to be all the representations with this infinitesimal character, which are bounded above, or which attain this minimal possible geometric wavefront set. We conjecture, and indeed in the paper that we've put out on the archive, we do this particular example. We conjecture that the weak Arthur packet is a possibly non-disjoint union of several Arthur packets, which are all trivial on the Wavefront group. And in particular, since they're trivial on the Wavefront group, they correspond to 2 commuting pairs of nilpotent orbits, and thus pairs of commuting semisimple elements. We conjecture additionally that these neutral elements should also satisfy this condition here. And that's the talk.
Thank you very much. Questions, please. I have a question about the example.
Yep. Just
from looking at the dual, I see that all the highlighted representations are numbered, their duals are numbered from 1 to 11. I mean, consecutive numbers. Is it just the way you numbered them, or
I think this
is the reason for that?
An artifact of the way it's been numbered, yes. Although yeah, I think as far as I can tell, it's maybe an artifact, although it is perhaps worth looking into. Yeah, so I guess that would perhaps give us some indication for resolving which Arthur packets would be in the weak Arthur packet. Yeah.
Okay. So another thing I can see is that in the so yeah, no. So one of them has in the column of row, one of them has a two, the others have only ones, the various powers.
Oh, so yeah, so this is representations of the joint component group, but I only include the saturation of the nilpotent orbit here. So this depends, the size of the partition depends on the size of the joint component group.
I see.
Oh, you mean in here, right?
Yeah.
What can you tell us a little bit about the techniques, the proofs?
Yeah, so to calculate these identities relating the canonical unramified wavefront set, the proof essentially. So the reason why we've done it for allIwahori-Spherical representations only is because we have this Q goes to 1 operations, which gives us representations of the extended Val group. So there's this equivalence of categories between allIwahori-Spherical representations and modules of the Hecke algebra, of the allIwahori Hecke algebra. Then you have this Q goes to 1 deformation for the standard modules, which allows us to boil down everything to statements about Weil groups. So sort of the key result in the paper is defining a notion of a wavefront set for Weil group representations, and then proving that, again, it has this characteristic that I mentioned, that sort of wavefront sets are dual to the unipotent parameter. So the unipotent parameter is the Springer support. So the central result we prove is that for a Weil group representation, the wavefront set is equal to the Achar dual of the unipotent parameter and the Springer resolution for that representation. And then we feed that backwards to get us how to compute this thing here. So the paper is actually, the structure of the paper is very simple. It's just proving that statement for Val groups is the big case analysis for the various types. But yeah, that's the gist of it, really.
This real infinitesimal condition that you have, infinitesimal character condition that you have, it seems to be serious, right? I mean, you can't do the cases of E6, I mean, E7 and E8 because of that.
Yes, that's exactly right. So there's this result. So it is a serious issue, like you say. The hopes is in our future research to extend it to the non-real infinitesimal character case, and we have a couple ideas on how to do it. It's going to have to be sort of non-trivial because of this issue that you mentioned, but some of the ideas we have involve sort of modifying Achar duality, but we haven't looked really into it yet, so we don't quite know yet how big of an issue it's going to be, if it's going to be, because I mean, we have this, the Hecke algebra for if you have a non-real infinitesimal character, it decomposes into sort of a matrix algebra of Hecke algebras where it is, and so there's some possibility for progress using this idea, but we don't really know yet how difficult it will be. Yeah.
You don't know how bigger class you can extend this to.
Yeah. I mean, we're hopeful that we can extend it to all infinitesimal characters. We just don't know yet. if it's going to be very hard.
It shouldn't be working for E7 and E8, right? So,
well, yeah. So this equality cannot hold. You're right, for E7 and E8, but we expect this should always hold. The conjecture is that this should always hold. So maybe we can do that for all the cases at least.
and there is this work of Jiang and Liu that they do global stuff.
Mm-hmm.
I mean, they really need more than just a real infinitesimal character.
Yeah,
they were done, but I mean, in general, it would be good to see if we can do, I mean, bigger than that. But that's going to take a while. I mean, that's
no, we're quite excited though. That sort of represented some big progress, so for us at least, and hopefully we're optimistic we'll be able to get some results for the non-real infinitesimal character case as well. But
okay.
Yes.
Thank you. It was a nice talk.
Thank you.
Okay. Any further questions? Okay, thank you very much. Next week, or not next week, next time, which is in 2 weeks, we will have a talk by Peter Bakic from Utah.